Tere tulemast Eesti Teaduste Akadeemia mereteaduste komisjoni laiendatud istungile. Me rikume nüüd keeleseadust lähema 2 tunni jooksul, selles mõttes, et edasine arutelu käib inglise keeles. Welcome everybody to the extending meeting of the Committee on Marine Sciences of Estonian Academy of Sciences. As an exception, we have today all discussions in English language, and the discussion is being broadcast over our website, and perhaps we shall learn after some time how many people have been virtually present. The topic today is in a way military, but not connected to the current war in Ukraine. It's about how the naval research could make use of Estonian science. So we have the guest today from Office of Naval Research Global. It's Science Director Patrick Rose. He's Science Director for Synthetic Biology. So you can understand how wide could be the spectrum of sciences what the Navy has interest to. The format today is something very usual, what we have in the Academy. About 20 minutes, plus minus a little bit, introduction from Dr. Rose, and then reflections, each about 10 minutes, possibly slightly shorter, and recommended not to become much longer. And then comes the most dangerous time. There is some option or possibility that wine could be offered. So be prepared to such dangers. With that, it's my pleasure to hand over the floor to Dr. Patrick Rose from US Naval Research. You're welcome.
Thank you very much. Good afternoon, everybody. Sorry, it's a bit loud. So I'm with the United States Office of Naval Research, and I appreciate the opportunity to come to the National Academy of Sciences here to speak to you about our organization, our program, and the opportunity for partnership in collaborating and exploring some fantastic ideas of advancing science and technology moving forward. So I will give a little bit an overview of our program, and I certainly have more slides than are allotted for the 20 minutes, but I will go through them quickly to be respectful of everybody's time. And I'll certainly make these slides available for the distribution to anybody who's interested in them. So the Office of Naval Research Global was created 81 years ago in partnership with the United Kingdom. Our organization's headquarters is in London, where I am stationed. I'm a civilian scientist for the US Navy. My background is in microbiology and immunology. I've been with the Office of Naval Research now for 6 years, and it's been certainly a fantastic adventure to be running this job. And I think you'll agree as you hear about our program and what we're hoping to accomplish, that there's some really interesting and intriguing opportunities to collaborate with us. And our goal is really stated here to advance scientific discovery and to make available worldwide scientific information. We truly believe that in partnership with you, that we can advance science and technology and disrupt the way we think about conventional challenges and issues. So much of this I've just mentioned again. So our goal is at ONRG Global, we're technology scouts. we're also technology enablers, and I certainly like to say that we're serendipity engineers, and that we like to fund innovative, disruptive research, especially on the basic research side, that might be agnostic to an application, and that we can drive forward and surprise ourselves in terms of what that application might be in the future. So a historical example, and then certainly something more contemporary that I like to mention, is some of the discoveries that have happened accidentally. So in the past, we had been funding research on microwave communications technology, and the legend has it, as these discoveries were ongoing, that one of the engineers had a chocolate bar in their pocket, and when they went up to a microwave emitter, they noticed that the chocolate bar was melting. And voila, you got the first inception of what was initially called the radar range, and now is the microwave that everybody has in their house. Truly a serendipitous event in terms of discovering where you had scientists and engineers pushing forward science for the sake of science and understanding how things function. And that's how we think about what we do. We're serendipity engineers. We're interested in fundamental research in advancing science and technology. We belong to a larger organization, which is a naval research enterprise. That is, our parent organization is the Office of Naval Research in the US, and then we are the Office of Naval Research Global, which focuses on the international engagement, so that is our primary goal. Our civilian scientists travel the globe looking for innovative, disruptive new ideas in terms of advancing science and technology. ONRG Global has many facets to it, just like the US Navy has and the Marine Corps has many facets to it. We do everything from maritime security all the way to disaster relief and humanitarian assistance, and so our sailors and our Marines cover a wide spectrum of responsibilities and a wide spectrum of challenges that they are struggling with and have to address. And so the science directors, part of the group that I represent, we look into the future. We look for science and fundamental research, again, agnostic to an application, to understand how we might change conventional thinking in science and technology, to disrupt the way science and technology is done and disrupt the technology that we're working with today. And so that is what we do. We're really focused on basic research. We like to say that we're interested in blue sky ideas, those blue sky crazy ideas that other funding agencies might not be willing to fund. We certainly do not want to compete with the European Union or Estonian national funding agencies in terms of what they're investing in. We want to collaborate with them and invest in those high-risk ideas that nobody else is willing to take a risk on, because that's where we see we can make the most difference, is investing in those ideas. And I know you have those ideas somewhere in your pocket or in your closet that you just haven't pulled out yet and are not willing to share. Hopefully you'll be able to consider sharing them with us and allowing us to take that ride with you. So we're a global organization. This just shows how we're widely distributed across the globe. We believe in international science because 80% of basic research is now done outside of the United States. And the only way for us to really enable science and technology is to be a trusted partner and an agent for advancing science and technology moving forward. So you have a unique perspective to provide here. You have unique environment that you have generated here. Certainly brilliant scientists that work here and that have established themselves. And we're here to facilitate their ingenuity, their imagination, to really drive science and technology forward from the fundamental level. We work with many universities across the globe. This is just an example of some of the universities that we engage in. And we're internationally represented and do many different activities, even beyond just funding basic research grants. In any given year, our organization is globally represented. So from the offices that we live and work from, we traverse the world and look for opportunities, which is quite exciting for us as individuals. And it's certainly refreshing to learn from your perspectives and unique approaches as to how to solve challenges today. ONRG Global is the first point of contact for you in terms of engagement with the United States Navy's broader naval research enterprise and their funding program. We fund, again, the early basic research. We take that risk to explore something innovative, something really ingenious, or something high risk that you think has a lot of potential. But we don't leave it at that, because we want to be a partner with you. We want to go with you down the path and further support research as it progresses and has the potential to disrupt the way we see the world today. And so this slide just shows you the ecosystem of how our organization works and what different potential opportunities that exist. So I come as a technology scout along with my team members to learn about what you have to offer. Then I turn into the funder for those blue sky crazy ideas that you might have to offer. And then from there I turn into a champion for you to advance the research that you're doing, because it is providing something very productive, something really refreshing and different than we have ever seen before. And we enable that through the Naval Research Enterprise and its establishment to be able to get access to collaborate with our scientists, to get access to other funding programs, so that the science that you're doing and advancing forward, we can help further facilitate. So what are we interested in? We align ourselves to the Office of Naval Research, our parent organization. The categories on the left are just the different departments that the Office of Naval Research represents. We generally, every couple of years, publish a framework in terms of our strategic interests and our investment in different technology areas where we see the need for more investment. This is a document that is publicly available, and I believe we're about to refresh that document. But if you take a little bit closer look in terms of what we're interested in, you can see that there's a broad spectrum of different topic areas that we're supporting and that we're seeking to further invest in. The topic areas still remain quite agnostic here in terms of the detail, and that is intentional, because we do not want to be too prescriptive in terms of the ideas that you might have to propose to us, and where you might say, this doesn't apply to any of the categories that you've identified, Patrick. Instead, we would want you to come to us and pitch an idea and be surprised as to what the potential is, and then try to figure out where it fits into our different categories. Because certainly something that we have to justify is that why are we using US tax dollars to invest internationally? But the point to that is we need to make sure that this is relevant to our mission and what the Navy's interested in advancing forward. Because we're talking about basic research, and basic research is generally agnostic to an application, it is easier to identify the relevance for it and certainly dream a little bit about what the potential applications would be. But I've already argued to you that we see ourselves as serendipity engineers. So if we're agnostic to an application, we might actually surprise ourselves and identify applications we could have never dreamt of before, right? To give you a couple examples, so as in my position as a science director for synthetic biology, these were some of the topic areas that we were interested in supporting. I will be transitioning away from the science director to a chief scientist position, and then moving on to hand this over to another one. But I do want to give you an example of my portfolio in terms of what we were investing in. And you'll see I'm going to be contradicting myself a little bit, because I said we're agnostic to application, but you'll see some examples of what application we're working towards after we've identified the research that we've been supporting. So these are just some examples of research that is quite interesting. It lists the title, it lists the grantee and the institution that we are supporting, and then there's a co-funding part to it, is where we are getting support from other funding agencies. So to the point where I was saying, I'm the technology scout, and then I become the funder of great ideas. Then I become a champion of those ideas and try to find other funding opportunities for you to continue the research that we have invested in, because we don't want to. We start the conversation with you. We're at the beginning of the partnership, and then we want to help transition that partnership to others to help support you further throughout the work. So these are just some examples of things that we're funding on the biology side. And these slides will become available so you can see these things, these examples further. But the point here really is that someone came with an idea to us that was difficult to justify to fund other funding agencies, quite sometimes a little bit more esoteric or risky in terms of their approach to things, and that's exactly what we were interested in. So when we make our decisions in terms of what we're going to fund, the key thing is really, is this something that is high risk, blue sky? If it's something that you have a lot of preliminary data for, and you can easily apply for European Union funding or your national funding agency, we're less interested in those things because we know that they will probably support that in some form or fashion. Whereas we're in that niche to take that risk with you, to go down an adventure and explore something that you think is really powerful to do. Excuse me. And so these are some of the descriptors of what we're really trying to look for here in terms of a research project. Okay, so I'm certainly here to come and learn from you and about the great science that you're doing and the capabilities that you have and the ideas. But I want to make sure that you understand that this is an equal partnership where we don't only want to learn from you what you're doing, but we also want to offer some opportunities for support for your research. And so the grant tools at the bottom are the examples of how we actually support funding. So the research grants are the ones that I mentioned. We fund 1 to 3 year research grants, basic research, agnostic to an application generally. Blue sky, crazy research ideas is what we're really pursuing. And we again partner with you so that you understand where you are in that process. I used to apply for basic research grants myself. I know that can be quite painful to write very long proposals, send them into an application, and then it goes into a black box, and then you may or may not hear a yes or no, and if you're lucky, you might get some feedback on this. We work very differently, and that is we start the conversation right from the beginning. So you reach out to us and say, hey, Patrick, I have an idea for different types of projects in an email, and then you point those out and say, which ones do you think would be interesting to the US Navy? And then we'll decide which ones are interesting. And from there, you expand it to a 3-page white paper. So that 3-page white paper will have a budget, a scope, a hypothesis, milestones and objectives. Because we're taking a lot of risk, we want you to go milestones to make sure that we're moving in the right direction. Assuming that you might not get to the very end of the project because it's such high risk, but showing that you're moving forward with the project. And so once we're at the same level and in agreement in terms of what that project might be, generally my staff or my team laughs at me because I always like to ask for more and more and more from the scientists because I know there's more inside of you in terms of the ideas that you have. But you have to keep me grounded and say this is not as realistic as you might think it'd be, Patrick. But once we agree to that, then we invite you for a full proposal. And so what that means is you expand your 3 pages to 10 to 15 pages of scientific discourse on how you're going to do the project, and then you submit it through our grants process. And the grant then comes directly to us. And because we've already agreed to the white paper, to the concept in the white paper, we then, as your champions, take that then to the Navy and say, yes, we would like this funded. That's the process. We will not invite you for a full proposal if we don't think we can get the project funded. Okay? We also fund workshops and conferences because we believe the discourse among scientists is extremely key to advancing science and technology, to identify new ideas, to crystallize new innovative approaches to things. And so we are generally quite happy to support workshops and conferences that you might want to facilitate here and bring scientists together. The collaborative science program supports travel grants, venue costs, publication costs. We don't support funding for food and drink. That's one of the key things. And then we don't support travel grants for individuals participating from the US because we're internationally focused, right? So we want to bring international scientists together. The last one is a visiting scientist program, so I'm going from bottom to top. The visiting scientist program is to engage you with the naval research enterprise. Let's say I see something that is quite interesting that we know the naval research enterprise, whether the laboratories or the funding programs are quite interested in. We'd be more than happy to send you up to 30 working days to the US to meet with them, to have some presentations, and we'll provide a travel grant for you to go there and support that discourse. And oftentimes that will crystallize or generate some new ideas because you're providing your perspective, your unique capabilities, and something that we might not have access to, and we might be able to provide something that you might not have access to, and then we generally create some new collaborations. And they might come back with some new ideas, or you might be coming back with some new ideas, and then we support those ideas. Okay, so those are the engagement opportunities, just so it's in black and white and you have this information. All the intellectual property remains with you or the principal investigator, however that's organized at your institution. We firmly believe in enabling you to be successful, to be productive, to create your startup companies, to identify disruptive new capabilities that the world hasn't seen before and take full credit for that. We don't fund US-based institutions, and one of our measures of success is how often do you publish, and acknowledge that this is something that you took in as a partnership with the Office of Naval Research Global. So we don't review your publications, we don't review your presentations. We want you to go out into the world and share the data that you've generated through this research that you've done moving forward. I have a couple more slides that I'm just going to skip in terms of some institutional information, more on the registration side that I won't talk about. So we get a lot of questions about what have we invested in, what are some of the products that we've developed over the years or invested in over the years. This is an example of many of the things that we started funding over time. You know, some examples here in the 1950s are we supported the research on the first digital computer project Whirlwind. In the 1970s, we supported research on lithium-ion batteries and GPS. And then in 2010, ONRG Global, for example, funded the discoverer of graphene research at the University of Manchester, who was then recognized for his discovery with the Nobel Prize. So we take a lot of pride in saying that we don't produce anything, but we invest in the great ideas that will lead to great discoveries and change the way the world we see it today. Certainly, there are other ways to celebrate success as well. So on the left is the Hamburg University of Technology. They came to us with an idea that nobody else was willing to fund. It was quite a fascinating idea on understanding coherent vortical structures behind fixed and moving blunt bodies. They couldn't get any funding anywhere else. We invested in them for a couple $100,000, and they came back and generated the data. And now the European Union then funded them with some additional research up to 1.5 million euros, and we think that is a success, right? Because we took the risk to develop a partnership with them. They showed the world that they could do something nobody thought was possible, and now they were being rewarded by other funding. And then on the other side is just an acknowledgement of some of the work that our funders have been doing in terms of what the result of that is. And that is recognition by their national societies or by the national organizations for very unique and distinct capabilities that they've done. So we celebrate success in many different ways. Ultimately, success would be to see something like this with your name on it. So we're really excited when Dr. Frances Arnold was recognized for her Nobel Prize in Chemistry a couple years ago. And she mentioned, as you can see highlighted, that one of her first grants was with the Office of Naval Research. And so we think that is quite exciting because we can say we crystallized some really cool ideas and look what that led to. Ultimately, we would like to see you on this list of Nobel laureates that we funded over the many decades, where individuals came with some out-of-this-world ideas, didn't really know what this was going to lead to, and then subsequently were recognized for very seminal research moving forward. And that's the ultimate measure of success for how we've accomplished our mission. Lastly, I just wanted to remind you again then of what we're interested in. We're interested in pursuing blue sky disruptive ideas that challenge conventional thinking, right, focused on basic research in terms of being agnostic to the application, but we're focused on the mission for the US Navy. And we're certainly hoping to be your trusted partner, your partner of choice to explore opportunities in driving serendipity forward. With that, everything that I've mentioned today is on our website. You can follow us on LinkedIn, where we advertise and certainly celebrate the funded individuals that we funded. You can find out about our funding agencies. And lastly, I'll just say thank you. There's my email address. Please feel free to reach out. These slides will be made available to anyone who would like them. And I'm happy to take any questions if we have time to do so. Thank you.
Thanks a lot, Patrick. Some burning questions from the audience. Okay. Just 1 second.
Consider joint funding. For example, some funds would be ready to fund only if there is another partner. So do you do partners with other funds?
Absolutely. We always like to see our money go further. So partnering with the Ministry of Defense, for example, with mutual interest, mutual investment opportunities, yes, certainly would like to do that.
Okay. Actually, the other question is totally from different area. One of your slides showed different geographical regions you act on. There were also certain countries like Russia or China on that slide. How do you do cooperation with them, especially if it's about sensitive technology on military areas? Do you have any protection measures? What's your position there?
Yeah, so we only fund basic research, fundamental research. As I mentioned, we are, of course, very careful in terms of how we engage with various countries in what the outcome might be of that. But first and foremost, this just explains to you how we've traveled around the globe to visit different places to understand what science and technology is available. When there are opportunities to collaborate, we will certainly try to find those, but because we're doing fundamental research and we firmly believe that fundamental research should be published and open and accessible to all scientists, it's easier for us to engage, and that's our primary focus. But given how quickly the world can change, decisions will also have to be made how we partner with the different countries.
Thanks a lot.
Thank you very much.
Thanks a lot for drawing this big frame for this research, and I understood from here actually 2 messages. First message is that being funded by US Naval Research is a shortcut on the way of having Nobel Prize. One of the shortcuts. And the other thing which I would like to mention, you mentioned Hamburg University of Technology. I think the process what you described took place when its rector was Professor Edwin Kreutzer, who was also a member of the Hamburg Academy of Science and Letters. Now he was president of this academy, and he got a medal of Baltic Academies for driving cooperation between Germany and Baltic states. And now he moved into the position of the chairman of Council of German Academies. So our very good friends, the world is really small. Okay, so now we reflect on what has been said by providing some information about the research highlights, what we have in Estonia, and also I think part of our reflection is description of big picture of what happens here in the Baltic Sea and why the Baltic Sea is so unique in the world. It's only slightly larger than Chesapeake Bay, but it's very much different. So people have been ordered here in those reflections basically randomly. So it's my pleasure to give floor to Professor Kevin Ellis Parnell, who will talk about some general features of Baltic Sea and coastal science, what is driven here. Kevin, you're welcome.
Okay, thanks very much. I think today we're going to introduce from a number of institutions some of the work that we're doing in our respective institutions and groups focusing around the sea. And I'm going to be presenting some advances from the Wave Engineering Laboratory at Tallinn University of Technology. And I understand that Patrick has talked to other groups in the university this morning. I'm going to be concentrating on, I'm going to be concentrating on four main areas, looking at waves, marine hazards, coastal and nearshore processes, and not to a much lesser extent, current-driven water transport. The highlights, I think, and the main messages that I would like people to take away are going to be in blue. And these are the things that I'm going to be concentrating most of my time on. This is really my main message. It's the summary, but I'm going to put it right up at the start so that the context of what I'm talking about is clear. And that is, the coasts of the Baltic Sea are not textbook coasts. If you learn about coasts in a standard university environment, reading the standard textbooks, and then come and try and work in the Baltic, there are going to be some very big surprises. And to actually get things right, we really have to understand these differences if we're going to make effective use of the science for management and other purposes. So here we have the Baltic Sea, just illustrating the countries that are around it, and obviously there are some geopolitical considerations that at the present time make the Baltic perhaps particularly important and interesting. I come from the other side of the world, Australia and New Zealand, and I've just put a map here just showing Tallinn on the left, highlighted in green, and the antipodes of Tallinn on the right. Now, instantly we see the effect of place and why place is important. The red dot shows a location well to the south of New Zealand that pretty much everybody would regard as being completely uninhabitable. Here in Tallinn we have storms, we have relatively short period waves. Down there in the Southern Ocean things are entirely different. Now it's a trivial example, but it just shows that place always has to be considered, and indeed I'm a geographer by training, and place becomes the essential way of thinking. When we come back to the Baltic Sea, we can divide the Baltic into two halves based on a range of variables. The first one here are the rocky hard coasts to the north and the sandy and soft cliffed coasts to the south. And I don't know whether yours is doing it, but my screen disappears every now and again, so I apologise if I pause. And that particular division is reflected in a range of other variables. For example, this one that shows the southern shorelines being essentially erosionary or stable, and the northern shorelines being essentially stable or accretionary. And a large part of that is the geological history or the sea level history, where in the north we have a relative sea level fall still going on. To the south we've got a relative sea level rise, and Estonia sits somewhere right in the middle. So we can't automatically just think about sea level rise when we're thinking Baltic environments. Here's another Australian surprise, or a surprise for an Australian. I'm very much used to seeing beaches like the one on the left, where you've got debris lines, where you can very clearly see tidal strand lines. Come to Estonia, I saw exactly the same thing. For the very first time, I got a bit of a surprise. Well, here are some tides, but of course, the Baltic is essentially non-tidal, and these strand lines reflect something entirely different. Again, a trivial example, but it just shows how something that you might read about in a textbook, come here, things are a little bit different. So the Baltic Sea coasts operate very differently to the textbook coasts, and here I've just indicated a difference and some implications. Almost no tides. That means that elevated and indeed very low water levels can remain for long periods of time. Water levels operate at different time and space scales, which means the effects of storms can be massively amplified over that which you might expect. Waves are directly influenced by local winds. Swell is limited. Swell dominates many beaches around the world, so that the wind direction during a storm strongly impacts the effects. And there are some already observable long-term changes in process drivers beyond those which are characteristically thought about, like sea level rise, things like water level extremes increasing, wind direction changes, which we know are happening, and things like sea ice changes as well. And all these things can have a very significant impact on coastal morphology. One of the most important things about the Baltic Sea that we really have to know about is the fact that wave periods are short. 3 to 6 second period is typical. Swell is essentially insignificant, and some of the implications of that are delayed wave refraction, which means waves approach the coast at a very high angle, which has implication for alongshore sediment transport, so that it is perhaps more important than in other environments, and disruption to it can cause significant problems. The whole classic textbook concept of beach cut and fill are far less relevant in this environment, and certain variables achieve perhaps more significance under these conditions, and one is wave setup, where we can get unusually high wave setup for sections of the coast, but it vastly depends on the wind direction at the time. Some more things are related to this variable. Minor changes in wind and wave direction can lead to vastly different coastal outcomes, and we know that wave and wind characteristics are changing. Just as an example here, we've got a diagram on the right-hand side there that shows that there has been a dramatic increase in the proportion of wind and storms from the southwest, and that has clearly major consequences for the eastern Baltic states. Another thing that's perhaps very different to many other coastal environments, and that is that geomorphic work is concentrated on a very few days of the year. In Estonia, 60% or thereabouts of the energy flux arrives within 20 days, and as much as 30% of the energy flux arrives during the 3 to 4 most stormy days. That is, when you think about it, very unusual and has a number of implications. Firstly, a question we're often asked: can the Baltic be used for wave-generated electricity? And the answer is no. You can't use a situation like that where almost all of the energy that you want comes in very few days. Beach erosion and recovery cycles are not seasonal, but irregular and possibly multi-year. And textbook beach erosion and recovery processes essentially don't operate. With respect to extreme sea levels, there are examples of extreme sea levels in the Baltic which are statistically almost impossible outliers. We expect variables like extreme sea levels to follow a distribution, and most of them do. But you can see on the right-hand side of the green dots and the red dots some very unusual circumstances. Now, under those conditions, the effects of the storms are massively amplified. We can forecast these things based on processes operating at different time and space scales, but in terms of human hazard, we need to understand those. I've talked about extreme sea levels, but the other thing that we know, shown in the right-hand diagram here, is that extreme water levels are rising. And it's important to just have a look at the scale here. The red dots are 8 to 10 millimetres per year, modelled over about a 40-year period. Now, that is obviously going up and down, but the trend of nearly a centimetre per year increase in extreme sea levels in parts of the Baltic Sea is very, very significant. Here's the red line again, dividing the Baltic Sea into two. It's in a slightly different place this time. And here we're looking at sediment transport and sediment budgets. In the north of the red line, we've got very much small independent sediment compartments, an example of which is shown on the right-hand side here, where there is essentially no sediment transport between those compartments. In terms of sediment, what you've got is what you've got for a very long time. To the south of that, alongshore sediment transport is very important, and if you have a look at the numbers on this diagram, internationally, these numbers in terms of sediment transport ranging up to about 800,000 cubic metres per year are very significant, particularly when you consider the relatively low energy conditions of the Baltic Sea. These numbers would be more typical of a much higher energy location. And the other corollary of that is that a very minor change in the wind and wave direction has major consequences. And if there is a minor change, it could have massive consequences on the very existence of places like the Curonian Spit down in the Russian Latvia coast. Sediment transport obviously is very important to understand if you're thinking about doing something like this, which would be a massive expansion that's currently being considered for the Klaipėda port. Interruption of longshore sediment transport by something that size is extremely important. So, just coming back, I hope what I've demonstrated in that very short run through is that the coasts of the Baltic Sea are very different and we need to understand it very well. Thanks very much.
Thanks a lot, Kevin. Any burning question at sight? Oh, he just denies questions. Okay, that's good. That's also enough. That's also fine. So the community of speakers was hit by COVID in the sense that some of us must be isolated. I hope we have now at least internet connection with Dr. Georg Martin from Estonian Marine Institute at Tartu University. He's expert in marine biology, and I hope very much that his message will come through. So Georg, if you hear us, the screen, the entire virtual screen is now yours for about 10 minutes.
Thank you very much. So I hope you can hear me. So yeah, I'm very sorry I was not able to join you today, especially in the afternoon, having a nice wine and a nice conversation. But yeah, but I have an opportunity to give my talk over internet. So I will have my talk a little bit in a different way. So I will try to highlight some of the research we are doing at Estonian Marine Institute, where I'm coming from. So Estonian Marine Institute is a research organization belonging to Tartu University. And nowadays in Estonia, we have actually quite a big demand for different types of marine research, both basic and applied. So we have a lot of economic needs, obviously, many of them connected to the blue growth, to renewable energy, and all other kind of economic benefits which might be gathered from the marine environment. Also, environmental issues like the Baltic Sea is one of the areas, marine areas, which is very much influenced by human activities. So we have a multitude of different problems here. So marine scientists are needed here to help society to cope with that, and also different social issues. So as education, cultural development, and other things. So we are all the scientists are very much needed in those things. So Estonian Marine Institute is the largest marine-related scientific organization in Estonia. So it's currently we have a little bit more than 100 people working here. We have 5 departments. I'm leading a department of marine biology. We are covering actually a very big variety of different topics, mostly biology, but also chemistry, a little bit of physical oceanography, both basic research and different applied research topics also. So in last 10 years, we have like more than 800 papers with authors working at our institute. So that's a quite active research community. So our infrastructure main office is located in Tallinn. So this is close to the sea, our capital city. But we have laboratories also in Tartu, which is our second biggest city and where the university is, our mother universities. And then we have a network of field stations around the coastline. So we are actually able to work all over Estonian coastline with different field works. We have quite extensive works also in our Western Archipelago. So research infrastructure includes research vessels. We have 6 medium to small size research vessels located along the coastline, but also on our biggest lake in the eastern part. And yeah, a lot of different kind of equipment, and also equipped labs like accredited chemistry lab and biology lab and other field and laboratory-based equipment systems. So some examples of our activities. So in the international scientific world, we are quite active. One of the quite in the framework of ICS, which is International Council for Exploration of the Sea, for example, we are participating in different working groups, and chairs of different groups have also are coming from our institute. Also on a Baltic Sea scale, we are very active in our regional sea convention, HELCOM, working in different working groups and on different levels as an expert and as a leading of different initiatives. So we have quite good experience here, qualification for in the Baltic level. So some of the examples of what we are actually working on. So currently the institute is involved in about like 50 or over 50 different research projects, both national and international ones. So it's very difficult to give a picture of or describe all of them, but I just picked a couple of them, which actually I'm myself also involved, so I can tell maybe a little bit more. But yeah, so one of the works would be involved lately quite a lot is a different type of habitat mapping in the sea. So there are different local scale mapping, like for example on a project level, like renewable energy projects, aquaculture projects, port developments, and also large scale mapping like basin or sea scale mapping, which is needed for example, reporting on the different European Union directives, and also for our regional sea convention. And we are quite a lot of involved in a method development. So we are trying to develop methods for in situ sampling, remote sensing, using different platforms. Also artificial intelligence and machine learning algorithm in modeling and spatial extrapolation of data. So we are involved in the national inventories, national-based projects, but also some international activities, Baltic Sea-wide. Some examples here. This is, for example, methodology we are working on. We are applying for a number of small-scale application or project-based application where we combine data sources from sonar measurements, point sampling, and applying different types of mathematical modeling, having for example, spatial distribution of different species or habitats or other features which are under interest for a certain application. Then also we are looking into using of different technologies like remote sensing, satellite, but also hyperspectral sensors, and applying this on the possibilities of mapping coastal or shallow waters what we have around here in the Baltic. Here is an example of a recent job or recent work for wind farm developers. It's an area west from Saaremaa Island, western coast of Estonian archipelago, and it's very exposed areas. Information from that area was actually practically missing before this project started, so we had the task of basic or first surveys with limited time and limited possibilities, and we got the information on the distribution of benthic habitats and benthic species and other features which are of interest for nature conservation, but also for the wind park developers. And this is an example of like a bigger scale work where this is maps of different habitat types, different classification systems which are needed for different national reporting in Estonia. This is covering all Estonian marine area. So another very important strand of work nowadays is connected to aquaculture. So we have a lot of interest in developing of the aquaculture in the sea. So currently we have like about 20 new applications for aquaculture in the coastal areas, but at the same time we have problems because aquaculture is supposed to be supposed to have a quite high environmental impact. So we try to develop different approaches how to reduce this impact and how to enable the possibilities of having this to increase considerably the aquaculture. And this is one example. Here is our experimental algae farm located also in Saaremaa, where we try to combine fish farming and, for example, algae farming or seaweed farming. So we have been involved also in different international projects, like here is inventory and development of different monitoring methods to follow the condition of nature values in Estonian marine areas. And we have a quite good cooperation here in the Baltic Sea area with different partners concerning that. And here example is cooperation, more wider international cooperation. We have good relations with Australian and New Zealand colleagues working with projects on describing the global patterns of benthic productivity and connections to the climate change. And here are examples of some research done from the west coast of Australia, where we can describe predict how the changing of climate will affect the productivity of littoral coastal areas. So, and in some cases, there are possibilities that this algal photosynthetic activity can either compensate on certain processes for the climate change effects. So there are many other projects also in a pipeline, and we are working with them. And I would like to be very happy to present them if you have some questions to that. So thank you very much.
Thanks a lot, Georg. It might be a bit complicated to continue discussion with you over internet, so we think that your very colorful and nuance-rich presentation reached everybody, and we can provide your mobile phone if you allow so.
Absolutely.
Okay, that was an important thing. Good. Then we thanks once more. We proceed towards coastal science again. Dr. Hannes Tõnisson from Tallinn University, but very much different scales, and I would say hands-on work on coastal processes. You're welcome.
Thank you. And good evening for everybody. And as you can see, I'm coming from the Tallinn University and talking about some coastal research in Estonia. And also I'd like to thank Ülo Suursaar from University of Tartu Estonian Marine Institute, who has been collaborating a lot also with the same projects here. So I hope, yeah. So I also thank Kevin, who was making some of the introduction already, but I just say a few numbers here, that the land uplift here in Estonia is up to 3.5 millimeters. It's relative to geoid actually, so at the moment it's a little bit slower because of the sea level rise at the same time. And shoreline is approximately 4,000 kilometers long. And the most important thing that also Kevin mentioned is that the sea level fluctuation without the tides here that we don't have is almost 4 meters. That means when we have a lot of westerly winds, the sea level can rise almost 3 meters. And when we have a lot of easterly winds, sea level can drop, let's say, a little bit more than 1 meter. So basically, these are completely irregular. So it just depends on the cyclonic activity and the patterns of the cyclones. And because of the uplift and also because of the sediment deficit, we don't have like a big dunes here. We have normally very narrow sandy beaches, and in the other places you almost don't see any movable sediments, and we don't have any dunes, just like a very, very small formations. But we have quite unique place here because last, let's say, 6,000 or 7,000 years, sea level has dropped all the time because of the land uplift. And as you can see from the next image, most of the land looks like there are some kind of stripes. So actually it's like a history book. So basically each stripe is describing some kind of past event. It's some kind of past storm. And inside of these, let's say, stripes, there are like pages of the history book. So, and today we are trying to find out what is written there. So if you already are looking at the, let's say, in more detail, you can see the area closer to the coast, which has like a red circle. You can see more visible ridges there. So these beach ridges are probably formed during the, let's say, more stormier period, and say with the bigger storms, higher storm surges, and the conditions maybe were a little bit more, let's say, marine. We had a little bit more marine climate. But when we go a little bit further inland, you can see some blue kind of circles, and there you don't see almost any ridges. So this was probably the period when we almost didn't have any storms. And later, when we go even further towards the land, we can see again larger ridges. So like Kevin was mentioning here, we don't have like a seasonal cycles here. We have some other cycles here that are like determining the erosion and accumulation process. So for that reason, we use the geophysical equipment to look inside of those ridges. So just to see what is inside. And why we are going there, the reason is quite simple. As you know, we have a land uplift. That means mostly in the sandy beaches we have accumulation. But these accumulation events are punctuated by some extreme storms, by some extremely stormy periods. And when you go to the coast and you see such kind of black sediments, these are heavier minerals. These are, let's say, more coarser sediments. And this is a sign of some kind of erosion, like some kind of erosional period or really strong erosional event. So what happens after the storm? Basically, the storm waves are carrying away the lighter minerals and finer grain sediments. And here you can see example of like a successive many storm and long period of erosion in this picture. And you can see very clear, like a black line of sediments. And why it's important? So as I told, mostly we have accumulation. And let's say a few months later, sometimes a few years later, the beach looks like this again, because all the sediments are later coming back, let's say when the stormy period is ending. And when you dig a hole here, you can still see the black line there very, very easily. Or if you go further inland and you don't have such a good excavator, you can use some kind of window sampler, for example, and you can still recognize those same storm layers here. Basically, all the storms or very strong storm periods are somewhere written under those big ridges. So now we are going there with the GPR, ground penetrating radar, and as you can see from the upper picture, those layers that are tilting seaward are much shorter, and the Aeolian layer on top is much shallower and smaller. And basically, this is representing the period when we didn't have many storms. And if you look at the lower picture, you see much larger ridges and also much more extensive layers. So these are probably the signs of very stormy periods or very big storms in the past. But why it's important? Okay, when we put it on a map, we are using OSL dating here just to see on what time these storms happened. And we saw that we had one very, very stormy period around 3,000, 3,500 years ago, when we had really large ridges, some of them up to 2.5 meters high. And then next stormy period happened actually about 800 years later. And if we go to the other places in the Estonian coast, we see almost the same pattern. So basically, for 800 years, we didn't have any proper storm in this period. We have been trying to look from the different proxies, but we couldn't find any signs that there have been storms. So basically, okay, my picture disappeared. Basically, for some reason, there was a big change, and this big change caused that we didn't have any storms for, let's say, half a thousand years almost. And then we had a stormy period again, and bigger ridges were forming. And we were also doing some separate study. Basically, we were searching the sand grains in the beach bogs. And there is a theory that when there is a more stormier period, the sand from the beach is also reaching to the beach bogs. And there is more sand grains in these layers when the period was stormier. So you can see from this figure that the same periods are actually coming out quite clearly, that the number of the sand grains is higher, also about 3,000, 3,500 years ago, and also around 2,000 years ago. And additional event that we have found is actually like a peak dune formation around 700 years ago, and later a few, let's say, additional reblown events. So this was actually really interesting, because I told you that we don't have any dunes forming here. And if you look at the picture on the top, on the lower left, on the picture, you can see that we have normally like this very narrow beach. So you cannot imagine how the dunes is forming. So that means there must have been some big change, for example, in the vegetation. We haven't found any reason why it should have happened. So, but we found that actually this is very clearly correlated with the period when we had this little ice age here. So in the wintertime, when the sea level, when the sea is frozen, there is also quite often the situation when the ice starts to move from the sea and it's piling up on the beach, and sometimes it's cleaning up all the vegetation, trees, everything for maybe 100 meters, sometimes even more. And when the climate is colder, there is less precipitation, and it's harder for the vegetation to fix the sand, and this is like a really good period for the dunes to form. But again, why it's important? We have now also been investigating the recent extreme storms, say around during last 20-30 years. We have been visiting the beaches during the storms. We have done the measurements of the sea level, what kind of formations are forming, how rapid is the erosion, what kind of layers are forming in the sandy beaches, just to compare what has happened in the past. And also in the process-wise, how fast some kind of development is taking place. Here is one gravel pebble spit that we have been following, how the changes are taking place there, and followed exactly what kind of waves have been there. We have done also the wave measurements near to our coastal study sites. And to conclude this part of the study, why we are doing it again, it's very simple. We don't know exactly what is going to happen in the future, and at the moment we have maybe 100, 150 years of meteorological data. Let's say in the best way, it's some kind of meteorological data, but in the geological way, we have data of the storms for last 6,000 or 7,000 years. So now we actually know what were the results of the storms, and we have comparison of today's storms. And at the moment we are trying to find out for example, what kind of conditions we needed to create the most extensive erosional layers in the past. and how likely we can have such kind of events also in the future. So it's all needed, let's say, in the future coastal management strategies or whatever reasons you are related to the sea. So, and that's why the Baltic Sea has been really useful. And we have done also quite many practical studies, and many of them jointly with the Estonian Geological Survey. Sten Suuroja is soon continuing on this topic, using also again some kind of geophysical equipment, all kind of geophysical equipment. And this is just to connect the sea and also the land, to see what we see in the sea bottom and what we see on the land. So because we need different equipment in the sea and in the land. And here is just one example of, for example, one research near the harbor. We have done some work just for the harbors. And you can see how we have been using the drilling data that has been done near the harbor and to see actually what kind of layers we have. For example, the lowest layer here is a limestone. On top of this is a really bumpy till layer, and on top of that is warped clay. And then the highest part, sometimes we have some sand, some malleolite, and some very fine sediments, sometimes mud. And if you put all the profiles together, we can actually see the pattern, how the sea bottom is looking like. And if we are using basically all this data is not just a picture, it's all with the coordinates and depth, and we can draw the maps in the sea bottom in what depth we have different layers. It's also important if we want to go to the past and see how the past processes were going on, just to reconstruct the conditions in the past as well. So for example, how the different surfaces are located near the, for example, harbors, etc. And finally, here is also additional study where we also map the bottom sediments in the sea bottom. And if you look the left part is closest to the coast, and the striped one, this is a till layer. And here you can also see how the processes are going on. Basically, near the coast, there has been erosion from the till. The sediments are carried towards the sea. There is sand, and also there is a narrow part where this warped clay is exposed. This is the most nasty thing actually in the Estonian coast, especially for the harbor development, because it's in the sea bottom, it looks like quite okay, but when you are doing some vibration or something like this, it turns like to a liquid or something like this, so it's not carrying almost anything. So it's very, very important. So, and shortly I think it's all, and thank you for your attention.
Thanks a lot. Words written on sand and disappearing with the next storm. Any burning question? Okay, then there will be more questions during coffee time.
Mm-hmm. Thank you.
Thanks a lot for making very clear one thing, that climate in the past was not necessarily stationary in terms of in a statistical sense. So it actually raises a fundamental question: what climate models can tell us if they can't reproduce non-stationarity of climate in the past? Just to explain what may have happened is again change in wind direction. So the rifts and dunes, what Hannes was talking about, they're very sensitive with respect to from which direction wind is coming. They are less sensitive to wind strength, so it may have happened in the past that the wind direction was completely different, wind direction in strong storms. But anyway, we can't assume that climate in the past was stationary in statistical sense. And this is something which is really fundamental for the future. So another speaker today is now staying in isolation because of COVID. This is Professor Kalle Olli from Estonian University of Life Sciences, which is basically agriculture university, but he is expert in marine microbiology. So Kalle, if you are there, the screen is yours for the next
I am
minute.
here.
Welcome, very nice.
Thank you.
Yeah.
So different from the others, I do not show you any slides, and hiding now in my summer cottage on the southern tip of Lake Võrtsjärv. I have a marine biology background myself, phytoplankton particularly, and I have been working in earlier times of my career in the ocean, quite little on the Baltic Sea, but quite some time on the northern seas, Arctic Ocean and the Barents Sea. And what did I do there was carbon cycling, sediment traps, vertical flux, and how it is regulated. So in a way, it is kind of related to the climate also. I then switched to lab experiments and coastal experiments, and finally, these days, I demolished even my lab, and I'm doing data analysis only. Personally, I think there's so much data out there in the world that it has to put some value on it. But a big change happened in my career a few years ago when I took up a position at the University of Life Sciences, and I'm administrating now a department titled Hydrobiology and Fisheries, and it focuses on freshwater, lakes, rivers, mostly, and it's kind of almost 50 people, academic and non-academic altogether, also mixed basic science and applied science, and there's all kind of things what people do there. I mean, the working groups are size of 5 to 3 to whatever, 6 or 7 even. And one of the things what I feel is quite intriguing is this monitoring. It sounds a little boring, but if the life of the biota have been analyzed and numbers worked up for 60 years sometimes or 50 years, it starts to talk quite a different story. And I feel it personally very challenging. It's not just measuring temperature, salinity or something, but it's among species level data, quantitative, and coming from such a long time. So the interest there is, if the 60 years is enough to cover some type of a climatic changes already, like wind strength changes or water level changes, how does the biology and the communities respond to that? So that has been my recent interest, and I just do everything I can to keep this monitoring going on. But there are other groups out there, and carbon cycling in relation to climate variability in the lakes has been quite an active part. Especially what they have found was the role of methane metabolism in the lakes. So the lakes usually in Estonia are all eutrophic, full of mud. There's quite a bit of methane productions there. So how that enters into the food web has been important. These days they have also switched to nutrient cycling, nitrogen, but also phosphorus. With the nitrogen cycling, they have found out that it's actually the winter ecology, what may be quite interesting, like it is now. If I look out there, the lake is ice covered, and maybe in the future we don't have so much ice covered lakes anymore. So it's the last time maybe to study how it works. And when it comes to the phosphorus cycling, it's all driven by the proposed phosphorus crisis in the agriculture in the future. We know that to keep the food safety, we need to produce food. For that, phosphorus is absolutely needed. While nitrogen fertilizer it's just a question of energy. For the phosphorus, it tends to be fossil sources. So we want to, earlier or later, we may run out of that. So how to cope that, how to recycle the phosphorus, how to reduce the phosphorus losses, both for the benefits of the health of the lakes and rivers, and also for the human food security in the future. We also do lake food web modeling and all those nitty-gritty little small details, what you can imagine a complex planktonic or benthic or mixed food web could look like. Modeling is one part of our activities. Needless to say, fisheries, freshwater fisheries and valuable fish like eel and pied perch seem to be in the focus here, in cooperation with the fishermen. That's mostly applied research done in the fisheries. And to my great surprise, we also do have some smart young dudes who do, I would say, opportunistic research. The university as a whole has highlighted a term, the circular economy or bioeconomy. So sometimes it kind of departs from the traditional hydrobiology or even any kind of water-related science. But who cares? I mean, if it just is cool things. So they started, or we started kind of how to give value to low, small fish, which fishermen get by bycatch. So usually they throw it back because they're not really allowed to. It's too much hassle to bring it on the shore. So how to give some value to that animal protein so that they wouldn't throw it back, and all kind of crazy ideas came out of that, from quite cheap composting to artificial skin and plasters and whatever. Then there has been some extensions from these animal proteins to other polymers like chitin, which can be collected from here and there. It's actually one of the most common polymers in nature after cellulose, I guess. But how to put value into that. And even to fungi. Fungi are made of chitin in most parts, and that has led to innovations like mycoplast, where you can make furniture or whatever out of fungi. So those research fields to me seem extremely exciting, although they are completely out of the mainstream of what we should do by the title of our department. But why not? I mean, people, especially the young ones, they're innovative and they try this and that. And one day I will just give my head that something really, really smart and clever comes out of that. Looking. Okay, I think I will stop here. I hope that Tarmo, you maybe are in a time limit, so maybe I call back some time to you. Online, then no questions, I expect. Right.
We can ask questions online because you were sparing a lot of time for everybody here. So
At your service.
I think that this is exactly what Patrick is looking for, something which is absolutely crazy, but which has potential to change the world. So if there is no burning question now, then can I share your phone with Patrick so that he could contact with you and ask for details?
Sure.
Great. Then, it's about how to connect scientists and policymakers, how to measure the connectivity. And there's a good indicator. It's the amount of scientists' phone numbers in smartphones of policymakers. It's a clearly measurable indicator, and that's one of the outcomes of today's meeting, I think. So we now go on, so to say, in depth into the Baltic Sea. It's about marine geology, and that's Estonian Geological Survey. And I think that Dr. Sten Suuroja is now risking to take the floor. I expected that you send your director as female here, but okay, that's what's called the gentleman's behavior. Okay, you're very welcome.
Okay, I like to show some slides about the marine geology in the Geological Survey of Estonia. I know that our director wants to say it, that we are a very young institution. We maybe started, that's maybe 3 or already 4 years ago. And also we are very young, but also we have a very small staff number for marine geology. If I found, okay, yes. Okay, my picture is, okay, now I have picture also here. We have a quite small staff, but as you see it, we have almost all of them have PhD degree, and we have also some advisor for other institutions, and we have very good cooperation with all our universities, and we are very plenty to offer our supervising for students, and also we are involving the students during summertime from our field works or marine works. Okay, yes, we talk much today about our location. Of course, Estonia, very special location by geological matter, because we are exactly locating between the crystalline basement, the Scandian shield, and between the East European platform. Therefore, our geodiversity is quite big, and also our marine area is very, very large. And if you're looking at how much geological information we have today collected, if you see there are two types of lines. These lines are marking the seismoacoustical profiling, which is a main, okay, I confusing these buttons a little bit. Okay, now it's back. It's these gray lines, they are marked data which we have on the analog format. It means that this data collected some 20, 30 years ago, and these magenta colors, this marks which kind of data we have nowadays in digital format. As you see, we don't have much in nowadays format. But the older data, which, for example, which was collected in the Gulf of Finland area, it was quite good, because we have, for example, very, very, very good penetration instruments like this gravity coral. It was very long. It was like in maximum some 15 meters that we have penetrated all of sediments almost, and we have quite strong penetration for geophysical profilings also. And luck for the Norwegian grant, we digitized this map data some maybe 5 years ago already. Okay, and nowadays, of course, we have a quite modern technique that we have a full coverage of the seismoacoustic profiling. We don't have only in geological services, but we are also joined all geological instruments which are also able in universities, and we are using the one system to operate this, for example, from one PC if needed. Unfortunately, I can't see the picture here, but I have some problems, sorry. Okay, I go back a little bit. No, okay, it doesn't matter. Okay, I had maybe there was a picture about the vessel, Akoi. Now it appears that we don't have unfortunately our own vessel, but we can use different research vessel owned another institution. For example, we have using the Estonian research vessel Salme, Stockholm University vessel we used last navigation period, and this year we are planned to use research vessel owned by Maritime Agency, because all our equipment is very mobile. It doesn't matter if you have a small boat or big vessel. It's operational in both ways. And there you have some last or recent results. It's a geophysical profiling along the archipelago area. It's, as you see it, we have a very shallow water here, like between 5 and 7 meters in depth, but we are able to penetrate it to up to minus 15 depth level and to get very accurate picture of the sedimentations. Okay, And this is some 3D model of this area because we don't have absent any geological data previously from our archipelago island. Now you see, as I said, in left picture, you see the seabed relief. It's quite flat, but on the right picture, you can see it. We have a very nice bedrock relief, which very well. There are lots of canyons and depressions, and it's a very new for us that it's talking us a lot of story about the late glaciations and then the development of this area after the last glaciations. And of course, in this area, we also doing some applied geology if needed. Hannes talked about the harbors, but with Hannes we also made some investigations there for connected with fairways, because there are lots of sand movements occur on this area because erosion limit is quite high. It's needed to know the background of these sediments, and then we can take some plans for dredgings for these fairways in the future. And coastal monitoring also in our table, we are responsive for state coastal monitoring program. And as Hannes showed that they are using the radar on the mainland, but we are more and more close to the seabed to offer a new methodology to make coastal monitoring also from sea areas. And there we also made some project to maps marine environment and nature. Okay, and then also the environmental investigation or research is important. Nowadays, marine geology goes closer to environmental things, and there are just some sample how we are collecting the data for environmental status. And then we can determine some threshold values which needed for different marine strategies. And of course, already was talked that we have nowadays big pressure for maritime use. And as you see on the left pictures, there are several offshore wind farms area as planned, and we are already collected some existing marine geological data for this work, and now we are also starting to digitizing also the older data to give some basic data for these activities. And of course, we don't keep the data not only for our house, we are responsive to make it for public, of course, and there are samples why we are dealing our data to this EMOTNet geology program, which is a pan-European marine information collecting portal or place. And there are many different layers, and we are responsive for all layers. We are sending the data annually for this portal. And that's all for me. There are just a couple of 2 pictures of our activities from last week with Hannes. That, you know, we don't have big research vessel. We have in winter time at least ice cover, and then we are using it like drilling platform. Thank you.
Thanks a lot, Sten. It's a stronghold of Estonian marine geology. And if there are no burning questions now, we will get them in about 7 minutes. Don't worry. You will get them. Thanks a lot to all speakers. Until now, I was not able to resist temptation to add at least one point. And the point is about identification and localization of. Okay. Okay, detection and localization of vessels which are around on the sea. So You can hide your vessel against raiders by stealth cover. You can make it extremely quiet, but you can't avoid producing surface waves. You can fight with your enemy, but you shouldn't fight with Newton's laws. So the pattern of waves what ship is creating is very nice to look at, and it's not so easy to measure it. So it's possible to measure it at one point, location, and typically people measure it by looking down with some echo sounder or something. What ships can do in proximity of big structures, so ships which are running in a relatively small channels and quite reasonable ships, they may bring down water by more than 2 meters. And this is really inconvenient if you are swimming or fishing that's just next there. And you see that ships always create some pattern of waves which you can follow. You can interpret this pattern, but the pattern has several absolutely repeating features. It's universal. And if you put either a sensor for elevation or sensor for pressure, you can get a cross-section of this kind of signature, and this signature is necessarily created by any object moving on sea surface. So now the art is how to interpret this signal of just, say, pressure sensor. So if you put a sensor, you see a sequence of fluctuations, either of sea surface, water surface, or pressure record. But if you apply a simple mathematics, trying to separate when different waves of different frequency are arriving, then you see a sort of L-like feature. You have a bass tone, which is more or less constant, the same frequency, same period, and then you see a chirp signal, which is becoming higher and higher. So this kind of L-type structure tells you absolutely everything about the ship. How rapidly it's going, how far it is, and even in which direction it's going. And moreover, this kind of picture portrays a specific ship. So those simple L-like structures are relatively slowly moving ships, and more complicated phases are coming from faster ships. So it is really possible, and we have done that. We have found picture of every ship which is sailing all over the Tallinn Bay. And just looking at this representation, we can say which ship was there, and of course, where it was, when it was, where it was sailing, and at which speed. So it is a sort of natural speed camera. If a ship is speeding, you can find it based on this record. And this is only based on Newton's law. More importantly, using an array of sensors, at least 4, but better 9, you can quite exactly specify the exact sailing direction. And we have done that. It's a simple mathematics. And by installing this kind of small batteries of almost trivial equipment, just pressure sensor with some mathematics, you can get a full picture of all ships which are sailing at a distance of a few kilometers from the coastline. And the accuracy of this procedure, you can see the red dot is a position of pressure sensor, and light blue dot is where we thought the ship was, that's calculated position, and the red red square is where it was actually as measured. So this kind of thing, simple system, could give you a recognition possibility of everything what happens in coastal area of a marine country. I think that in some time this will replace radars to some extent, and to repeat that you can hide yourself from radars, but you can't avoid producing waves. So don't fight with Newton's laws. Thanks once more to everybody. It was a very nice seminar. I learned a lot in this condensed form, and the broadcast ends now, and all people can now face the danger of having coffee and possibly even something more, about which you were warned, and I repeat, you were warned. And what about time arrow? What we always say here, we can forecast the future, and the doors into future are just behind me, and they will be opened just now, the doors into future, forecastable future. Thank you very much.